state space representation using observable canonical form. Let us take the transfer function in polynomial y of s by u of s, which we know already. So numerator we have bn s power n plus bn minus 1 s power n minus 1 dot dot up to b naught. The denominator I have s power n plus a n minus 1 s power n minus 1 plus up to a naught. So this is the transfer function which we have taken, and let us take n is equal to 3 and see how can we develop the observable canonical form. So y by u or y of s by u of s is equal to numerator will be b3s cube plus b2s square and b1s plus b1. So denominator is we have already s cube and a2s square plus a1s plus a naught. So in this case I want to rewrite this transfer function such that we can build the signal flow graph. So for that what I can do is take the transfer function, and the denominator we have s cube, take that s cube common, and also the numerator you take the s cube common. Then what will be the remaining? Then y of s by u of s, it becomes b3, already s cube is there, plus b2 by s plus b1 by s square plus b naught by s cube. The denominator we have 1 plus we have a2 by s plus a1 by s square, a naught by s cube. So in the denominator again I can write it as 1 minus of all minus terms, minus a2 by s minus a1 by s square minus a naught by s cube. When you look at this, this is in the form of Mason's gain formula, which means, so numerator terms are your forward paths, denominator terms are the individual loops, and here assume that there are no non-touching terms, and also the delta 1, delta 2, delta 2, delta 3 in the Mason's gain formula, and here it is going to be 1. So with that assumption, then I can build very easily the signal flow graph. Now how many forward paths available in this case? 4 forward paths available, and all the forward paths I can take from the input side. From input I will take all 4 forward paths. Of course one will be the straight and remaining 3 on the top of it. Then denominator, if you look at, there are 3 terms, which means 3 individual loops. All my individual loops will start from the output side, then I can connect all the outputs with the coefficients which are available to me. Now before going to that, we know the order of the system is 3, so it is a third order system. Similar to the block diagram, here also we need to take 3 integrators. Integrator is 1 by s. All the integrators you can place like this, but when you are numbering, in this case you number from the right side to left side. Let the first integrator is output is x1 and it is x1 dot, x2 and x2 dot, x3 and x3 dot, and all the nodes we can take like this, and input node is u and output node is y. Now, so once the node is available, then as I said, the forward path should be drawn from the input side. So from u, then I am going to draw like this, you can see very clearly. So one forward path is a straight which is available, the other forward path is like this, and the second and third and fourth. Then individual loops which I am taking from the output to this, because the nodes, corresponding nodes are available, and for the nodes then I can draw very easily. So once the signal flow graph is available to me, then it is writing the equations. So how to write the equations? First write the equation for the output. So what is y? Y is x cube plus b3u, x3 plus b3u. This is equation of the output. Now what are the state variables? State variable equations, we need to write the equations at x1 dot, x2 dot, x3 dot, and whenever you write the equation any one particular node in signal flow graph, you consider all the incoming branches, and using the incoming branches we can write the equation. Now when you write the equation for x1 dot, it's very clear there are 2 incoming branches, b naught u minus a naught y, and y which is already available I can substitute here. Then I will be getting it as a x1 dot is equal to minus a naught x cube x3 plus we have a b naught minus a3 a naught into u. So this is your x1 dot. Similarly I can write x2 dot, again there are incoming branches too, and those incoming branches we can write x2 dot as minus a1y plus b1u, and of course if we closely observe one more input also there, that is x1, so plus x1. So 3 branches, with these 3 branches then I can write x2 dot. Then the x2 dot is going to be x1 minus a1 x3 plus b1 minus b3 a1 into u. So this is equation 2, that is for the second. Similarly I can write for the third also. The third x3 dot is you have b2u plus x2 minus a2y. So you take the y and substitute here, and you will be getting x3 dot as x2 minus a2 x3 plus b2 minus b3 a2 into u. So with these equations then I can easily write state equation. Here I have x1 dot, x2 dot, x3 dot, A matrix, and what are the entries? Let us do the entries later. x1, x2, x3 plus b into u. U is 1. So when you look at that equation x1 dot, therefore we have 0, 0 minus a naught, and here the u term you have b naught minus b3 a naught. That is the first element in B matrix. Similarly x2 dot is we have 1, 0, and also we have minus a1. Then in B matrix we have the entry like b1 minus b2 a1. Similarly third one also we have 0, 1 and minus a2, and b2, the entries of B matrix, the last element is minus b2 and minus b3 a2. So this is a B matrix and this is the A matrix, and using the output equation then you can also write the C matrix and D matrix. Let us see how to write the D matrix. D matrix anyway it is Bn and B3. So C matrix is nothing but 0, 0, 1. So 0, 0, 1. So output equation, we know that output is nothing but x3 plus b3u. So therefore C matrix is 0, 0, 1. D matrix is B3. Now we can also generalize this as like your CCF form, OCF form. You can generalize it. When you generalize it, what is the A matrix? Now you are having first column 0, 1 all zeros. The second column 0, 0, 1 all zeros. So this 1 is shifting like this. And what will be the last before column? All zeros, the last element is 1. And what are the entries of the last column? Last column are minus a naught, minus a1, minus a2 up to minus an minus 1. And look at the B matrix is your b naught minus bn a naught, and bn minus bn minus 1, b1 minus bn minus 1, a1, and so on. So we will be writing like this the B matrix, and C of course it is 0, 0, 0, last element is 1, and D matrix is Dn. So when you observe the general form of OCF form and general form of CCF form, then we can have the relation between these two. What are the relations? For example, in controllable canonical form, the ABCD matrices are AC, C suffix, AC, BC, CC, DC. In observable canonical form, A naught, B naught, C naught and D naught. Now what are the relations now? From the two, you can see this is your controlled canonical form, this is your observable canonical form, A matrix, B matrix, C matrix, D matrix. When you compare, then we can easily write the conclusion that your A naught means observable canonical form A is equal to AC transpose. When you transpose it, you will be getting the observable canonical form. B naught is C transpose and C naught is B transpose, where D is nothing but a D transpose. So this is what the relation between OCF and CCF form. So one is available, other one we can easily get with this transformation, and we can say that OCF and CCF are dual each other.